Hello. Am I audible? Yes, I think I'm audible. So last class we discussed ASIC design flow. In the ASIC design flow, we discussed that we started from the design specification. After the specification, we go for circuit designing, that you will design on the schematic editor window on Cadence, and then we will go for simulation, that is connected with ADE assembler, that is analog design environment assembler or explorer, and you use a spectre. Okay, and here we, after that we will simulate it. If simulation is okay, then you go for layout, otherwise you will go for a schematic. Okay, and this process is done by the analog circuit designer, and this part is analog circuit designer part. Okay, once you go for, after the completion of the analog circuit design, we will go for layout design. As you know that circuit is not fabricated, the layout will fabricate, and you convert your schematic in a base layers. Okay, that have a layers like NVEL, P implant, N implant, OD. Okay, lot of layers we have, and metal 1, metal 0 to metal 7 or metal 9 as per specification suggest. Okay, and after that you convert your schematic into a layout, but in a layout you must be focus on that कि your transistor should be arranged in a such a way कि that it will take a minimum space, and the routing should be very good so that it will take a minimum IR drop. Okay, and of course if the routing is very good, you will use a minimum metals. As per metal will be high, let you are using metal 0. Okay, you are designing a one layout, and that layout is completed in metal 2, metal 0, metal 1, metal 2. If you are going for metal 3 and you can complete in metal 2, you can reduce the cost with thousands of dollars. As per that metal you can increase, as per the cost will increase. Similarly, if you are using a area, higher area, if you are not compact your layout, you are not arranging properly, so the cost is directly proportional to area. Okay, so that's why layout is very important once you go for the layout designer. And after the layout design, you are going for the physical verification, that is Pegasus verification system. And the Pegasus verification system, we have a DRC and LVS. The DRC is represent the design rule check, and LVS is representing layout versus schematic. So in a DRC, that every tech node will provide the DRM, that is design rule manual, have a set of rule. Okay, you are designing a layout, you should have a minimum spacing of something, minimum spacing for something. Okay, everything is given, so that you are designing the layout on the basis of the DRC. You can't design anything from the layout. Okay, you should follow that DRC. Okay, that will be help to fabricate. If you are not following the DRC, your layout will not fabricate at the company, and the tech node will decide that DRC rule. Okay, and DRC always provide the minimum criteria, that is minimum enclosure, minimum spacing, latch up, pre-substrate, stamp error, float, these type of error they have, and deep and well. Okay, we will discuss once we start the layout, ST isolate, trench isolation. Okay, and after that you go for LVS, that is layout versus schematic. Of course, you are designing a layout of the schematic, so your layout should be same as your schematic. So in comparison of layout and schematic, you are comparison 4 things. That is, one is pin. You are using VDD, you are using VSS, you are input and output, just like a CMOS inverter. So you have your layout will be matched from the schematic pin. So pin will be matched. Second one, net. You are connecting the net. You are connecting PMOS to NMOS. The drain of the PMOS is connected to the source, drain of the NMOS. Okay, they are connected like in a such a way, or you are using any routing path. So the schematic routing path will be same as layout routing path. Okay, so net connection, it is very important, that should be matched. Third one is device. You are using a PMOS and NMOS, that should be same for layout also. You can't use 2 PMOS in a schematic and 1 PMOS in a layout. That should be same. And fourth one is parameter. The W by L of PMOS and NMOS, if you are using a transistor, you have a W by L, that should be same for layout also. So we will categorize LVS in terms of pin, device, parameter and net. If all four things are matched in comparison to a schematic netlist to the layout netlist, if both are same, then I can say the schematic circuit and layout circuit will be same. The layers as compared to your schematic, they are same. Okay. So these are the physical verification. After the physical verification, you are going for what? That is extraction. That is quantized extension. If you are extract your layout where that you have a that is parasitics, that is resistor and capacitor. Of course, MOSFET have a CGS, CGD, CDS, CGB. Okay, they have a lot of capacitance. So you will extract this capacitor and find it. Okay, that schematic provides some simulation. Same schematic, same simulation I will run for layout. If both have a changes of 5% or 10%, it will be okay. But the difference is too much higher than 10%. So we will change the layout or we are changing the schematic. So that's why I make a that if simulation after post layout simulation, if everything is okay, you go for GDS, that is graphical data system or graphical design system for tape out. If this is not okay, you go for layout or you are going for the schematic design. Okay. So if layout designer will correct it and it can be make such a layout that both simulation is correct, both simulation have a same with a have a difference of 5% and 10% in output, so it will be okay. And if the layout cannot do this, so a schematic designer do something on a schematic and then try to make it okay, that result will be same. Of course, we will follow the design specification always. We cannot afford that design specification will be different. Okay, you are thinking that bandwidth is 50 megahertz, your output, your simulation should be have a frequency of 50 megahertz or more than 50 megahertz. Okay. So these are the ASIC design flow. Okay, you can be analog circuit designer, you can be a layout designer, it's up to you. And after that, we are going for that is basic understanding of MOSFET. So as we know that we have a cross-sectional view of MOSFET, and where we talk about, okay, we have a 4-terminal device, that is gate, source, drain and body. So gate is fixed, body is fixed. If you talk about source and drain, it can be anyone. It depends on the power supply, that V1 and V2. If V1 is higher than V2, so V1 will be a drain in NMOS and V2 will be a source. If you talk about PMOS, now PMOS, the body is N-well and you have a gate and you have a source and drain. If V1 is greater than V2, so V1 will be a source and V2 will be a drain. Okay. So in a higher supply in NMOS become a drain, higher supply in PMOS become a source. Okay, so till now we discussed this part, and after that we discussed that VGS, the gate to source voltage, decide the inversion layer, because we are not talking about the depletion mode MOSFET, we are always preferring enhancement mode, because enhancement mode is behave like a switch, where that depletion have a already channel, it is always behave like a resistor. So 99% or 99.9% we always prefer that is enhancement mode MOSFET. Okay. So let's talk about the enhancement mode MOSFET when VGS is less than VTH. So VGS is less than VTH. I am talking about NMOS. So you have a NMOS. Okay. And this is the symbol of NMOS, and I am connecting here, that is gate to source voltage, that this is VGS, this is source terminal, and this will be a drain terminal. Okay, that is VDS. This is VGS and this is VDS, or you can make a cross-sectional view also. Okay, you have a MOSFET and you have a, this is P substrate, the body terminal is P substrate, and this is the silicon dioxide, and you have an implant, that is active area, that is N plus and N plus, and you have a metal. Okay. So this is gate voltage. This is, let I am assuming this one is source voltage. So this is the representation of the voltage supply, that is VGS. That VGS, the gate is connected with the positive terminal and source is connected with the lower potential, and of course this will be a ground. I am thinking in a way, okay, this is grounded. Okay, and you have another potential here, that will be VDS. Yes, this is your VDS. Okay, so this is a source and this is a drain, and drain VDS, that drain terminal is higher potential than source, where the source is grounded. So you can think like this or you can think like this. This is a symbol structure and this is a cross-sectional view. Okay, and if you are providing the gate to source voltage, so firstly start with that very basic thing. This is metal, this is oxide, and this is semiconductor. If you talk about oxide, this is behave like a oxide, and here you have that is a field oxide here. Okay, so what is the input impedance? If there is not a conductor, it is an oxide here, so current is not passing here. Ideally that gate current or input current is 0, but practically it is nanoampere or picoampere. Okay, so in a metal oxide semiconductor, we are forcing that we are designing a MOSFET in such a way the gate current is 0 ideally, and the input impedance is infinite. If you talk about BJT, in a BJT you have a base current, and base current is not 0 ideally, it have a current. Yes, but once you talk about MOSFET, in a MOSFET the gate current is 0. So if gate current is 0, that means there is a no loading effect. So if we are designing, just think in a way, okay, you have a, I am just thinking in a way, okay, you have a transmitter and you are taking that, okay, this is a receiver you have a transmitter. So this is receiving the data, or you can say that we have a voice signal, that is audio signal, and of course this signal is coming here with the MOSFET, with the amplifier. Let I am designing a circuit that is an amplifier. So this signal or this voltage will not reduce. Why? Because this have a no loading effect. The input impedance is infinite. The same voltage will be provided on the gate side. If you are talking about the BJT, that have a drop. Why? Because you have some base current. So this is the problem on that BJT. The input impedance is not infinite, but in a MOSFET you have an input impedance is infinite. So you can think in a way, okay, the input impedance is infinite, so you using that any voltage here, so there is no drop. That will be same for that. Yes, is it? Okay, so that's why MOSFET is very useful, where the input impedance infinite, it is scalable, it is very small in a space, in a layout. Okay, but if you talk about BJT is P and P, and it is very bulky. Okay, so that's why MOSFET is useful and very useful for you. And we are working from a MOSFET from a long ago period. Okay, and I think it will be continue. We are going for FinFET, but FinFET is not that much. But means that FinFET is in after 22 nanometer. After 22 nanometer, you can use a FinFET, but mostly analog circuit designer is designing on the CMOS basis or the MOSFET basis. Okay, so let's talk about this, that VGS is less than VTH. So what is happening? Firstly, you think that input impedance is infinite and the gate current is 0. Ideally, the gate current is 0. And if VGS is less than 0, if VGS is less than VTH, that you have a channel, but this channel is not that much enough to provide a good conduction in between N plus and N plus, in between source and drain. Means you are going a VGS is from 0 to some voltage to VTH. Means as per VGS is positive, this terminal is positive side, this is positive side, and due to positive and that the electric field is present due to the oxide and that have a negative, that will be provide a minority charge carrier from the body, and similarly from majority charge carrier from the N plus, and will form the inversion layer. And this is happening, but VGS should be equal to VTS, then only I can say that the good conduction will possible, the current can flow from source to drain. So if you talk about ideally VGS less than VTH, ideally ID is 0. But practically you have a some current, because it have a small amount of conduction. As per VGS is going on, as VGS is going on for reaches to VTS, a good conduction will form. But before VTS, it have a current that in between drain to source. And this inversion layer form a channel in between drain to source. Yes, everyone. Is it okay? And the drain and source voltage will decide that how much amount of current can flow. So I can explain in such a way, okay, if VGS is less than VTH, that ID is approximately 0. That is very small current. But if VGS is greater than VTH or greater than equal to VTH, that ID have a current. And this condition, if VGS is greater than equal to VTH, that ID is not 0, ID have a some current, and that will be decided by the region of operation. It have a two region. One is linear, one is saturation. It can be a linear, it can be a saturation. Firstly, you will check it, the MOSFET is on or off. If VGS is less than VTH, I can say that MOSFET is off, ID is approximately 0. If VGS is greater than equal to VTH, you have an inversion layer, the ID is not 0. The MOSFET can be in linear, can be in saturation. It depends on that condition. That depends on what? That VDS is less than VGS minus VTH, then MOSFET in a linear region. If VDS is greater than equal to VGS minus VTH, that is saturation region, and that is very, very important equation. Whenever you talk about the MOSFET, you are designing a current mirror, or you are designing a differential amplifier, you are designing anything, these equation only decide your node voltage. Okay, by this equation you can approximate what is the value at the node side. Of course, tool have a lot of specification. They have a lambda factor, that is channel length modulation. They have a gamma factor, lot of things in the tools. Tools will provide the exact answer as per your circuit designing. But by this analogy, you can understand what will be the node voltage. You can approximate what will the value at the drain point at the source voltage, at the source node. So these are the very important equation. Just think in a way that before VTS, that this is a NMOS equation. If VGS is less than VTS, that I am saying that the drain current is 0. And if gate to source voltage is greater than equal to VTH, means you are providing the gate to source voltage as much enough that you can form a good inversion layer. Or you can say that the majority charge concentration of the body is equal to the minority charge concentration below the surface. If both are same, so you can say that the concentration of both majority and minority will be same. So that will the point that is called the threshold voltage of the MOSFET. And if this is happening, the MOSFET can be act as a linear, MOSFET can be act as a saturation. And if you talk about VGS less than VTH, this is called as cutoff. Okay. So that linear and saturation, or linear is also called triode region. You can think in a way the linear region or triode region, both are same. So these are the triode region or saturation region. Okay. So MOSFET can be act as a linear region. When the MOSFET is on, it can be act as a linear region, it can be act as a saturation region. In digital, we never talk about linear and saturation. We always talk about switch on or switch off. But when you talk about analog circuit designer, in an analog circuit designer, you must have a basic understanding, okay, where is the MOSFET in a linear region, where is the saturation region, what will be the trade-off, what is the notch point where that MOSFET after that saturation and below that linear. Okay, so that's why in an analog circuit designer, you must know linear and saturation. But in a digital, if you are designing a NAND gate, NOR gate, XOR, D flip-flop, anything from the MOSFET by the help of CMOS or anything, that the MOSFET is act like a switch on, switch off. There is nothing of the linear and saturation. Okay, so MOSFET VGS is greater than equal to VTS, that ID is not 0, ID have some value. It will be decided by the linear or saturation. If MOSFET is VDS is less than VGS minus VTS, that MOSFET in a linear region. If VDS is greater than equal to VGS minus VTH, MOSFET in a saturation region. And both have a different current equation. So that condition is VGS greater than equal to VTH and VDS is less than VGS minus VTH. That means that MOSFET in a linear region, and MOSFET in a linear region, so that current equation ID is equal to mu n CoX W by L VGS minus VTH into VDS minus half VDS square. I am not going for that explaining that how that current will be formed, okay, where we required a charge equation that Q is equal to something value that mu n CoX. I am not going for that, I am just writing that equation. Okay, so if you are talking about that MOSFET in a linear region, the current equation is mu n CoX W by L VGS minus VTH into VDS minus half VDS square. Okay, means ID depends on VGS and VDS both. If you talk about saturation region, that VGS is greater than equal to VTH and VDS is greater than equal to VGS minus VTH, means the drain voltage is above than the one threshold of the gate voltage. So that is called as MOSFET in a saturation, and ID is equal to 1 by 2 mu n CoX W by L VGS minus VTH ka whole square. And I am just thinking a way, okay, there is no any channel length modulation, the lambda is 0. Yes, I am talking about the higher channel length, the lambda is 0, otherwise there have a 1 plus lambda VDS. So this is 1 upon 2 mu n CoX W by L VGS minus VTH ka whole square. If MOSFET in saturation, if MOSFET is that MOSFET in a linear, that ID is mu n CoX W by L VGS minus VTH into VDS minus half VDS square. So this is the way that you can understand that the drain current, it depends on the W by L gate to source voltage, And whenever you are talking about that analog circuit design, always we focus on the MOSFET in a saturation. If you are designing an amplifier, if you are designing any like common source amplifier, common drain amplifier, common gate amplifier, yeah, differential amplifier, current mirror, anything you are designing, you are thinking that MOSFET must be in a saturation region. Okay, so why that saturation is better than linear? We will talk about that the funda of transconductance. The transconductance is good for a saturation region, where that if you talk about linear region, the transconductance is not good. It's not a good value. Okay, so that this is a linear and this is a saturation. So this is a part of saturation. Yes, everyone, is it okay? So till now we discussed this part. Okay, just think in a way. Why FinFET ideally not used for analog circuit? Yes, okay, dear. That FinFET, it's not ideally they are used. Of course, FinFET is used, but FinFET required we required a lower technology. Not FinFET is working for a lower technology, where that you find that less second order effect, means you are talking about sub-threshold conduction. I have a example in this. If you know that is sub-threshold conduction. If you talk about the MOSFET, the sub-threshold conduction means VGS is near about VTH. We are trying that the ID is very, very small. That current is nearly about 0, that is nanoampere or picoampere. Okay. But once you going for a lower technology, if you are going for 180 nanometer to 90 nanometer to 45 nanometer, 55, 65, and after that 45 nanometer, you find it that sub-threshold conduction effect is increases. Means near VGS to VTH, the current is large. And you can think in a way, okay, you are using a laptop. And a laptop, you have billions of transistors, means you have a 10 lakh of transistor in a laptop. And that you are using a sleep mode you are using a sleep mode. Okay, you are providing that sleep mode in a laptop. So of course you have a leakage current, you have a current. Okay, the current will be dropped, but this current is not that much good, so that your battery will be drained out fastly. So in a sleep mode, that VGS is less than VTH, the current will decide that how much amount of current will decide from it is taken from the battery, will decide how much it will take time for drain out. Okay, so if you are designing with a 180 nanometer or 90 nanometer or for 55, 65 nanometer, the sub-threshold conduction, that ID is near about very small. But as per you are going for lower technology, like for 22 nanometer, at 22 nanometer, you will find that sub-threshold conduction value is very high. That current is very high. And if one transistor will provide a good current, and the billions of transistor, means 10 lakh of transistor or crore of transistor, 10 crores of transistor are present in your IC, so we will provide a large amount of current, where that circuit is not working, because VGS is less than VTS, that circuit is not working. So that will be a problem for a MOSFET. Okay, so you go for FinFET. So in a FinFET, you are thinking a way that the lower node you can work and where the sub-threshold conduction have an effect, but it is not that much as compared to MOSFET. But if you reduce the length, of course you will find that different parameter, that is second order effect. You will find the velocity saturation, you will find the GIDL, you will find the DIBL, that gate induced drain leakage, drain induced barrier lowering. These are the lot of effect introduced as per the lower technology. So if you are designing analog circuit designer, we are trying to reduce the second order effect. So how can you avoid this second order effect? You are using a higher length. So if you are designing a 90 nanometer, okay, you are working for a 90 nanometer technology, you are choosing the length is 500 nanometer for analog circuit designer, or a 1 micrometer. Why? As per length will increase, you will find that second order effect will be less. Okay, so that's why that the way we are talking about the MOSFET is all that till now we are using MOSFET for analog circuit design. Okay, if you talk about that IO circuit, ESD, or you are talking about the schematic trigger, op-amp, they all are designed with a MOSFET. As per the improvement of the technology, we can go for FinFET. Yes or no? So FinFET is not different from the MOSFET. You all are thinking in a way, just like we are moving from BJT to MOSFET, we will move from MOSFET to FinFET or FinFET to tunnel FET. It's not meaning that FinFET is coming, so that what will be happen? That same equation, you use that the equation have some changes. Yes, just like in a BJT you use a common emitter. In a MOSFET you are using common source. Yes or no? So that we are always following this funda from BJT to MOSFET to MOSFET to FinFET, FinFET to GFET. Anything is coming in a market that the gain we trying to make that higher gain. We trying to make the input impedance is infinite. We trying to that the output impedance is zero or infinite as per the requirement of the amplifier. That if you are using a voltage control voltage source, you are trying that output impedance is zero. If you are talking about voltage controlled current source, that output impedance is as much high as requirement. So it depends on the application there. So the FinFET will come or a MOSFET will come, there is nothing you will be worried. If the FinFET will come, you will be going to too much understanding for the FinFET. Okay. Till now we are working for a MOSFET, that's why we are focusing on only MOSFET. In a digital term we are going for FinFET. Okay, but in analog till now we are working on MOSFET only there. Okay. Yes, anyone have another question? That is gate all around transistor. Yes, GAA. Yes or no? Okay, subthreshold region is possible when VGS is less than. Yes, dear. The subthreshold conduction is possible when VGS is less than VTH. Okay. So if you are going for a simulation, VGS is less than VTH. If VGS is less than VTH, you always find the region 3. Okay. If you simulate it, I will simulate it on a cadence virtue. So I will show you that that cadence will represent you region 3, not a region 0, because region 0 is representing cutoff, region 1 is representing linear region, MOSFET in a linear region, region 2 is representing saturation region, region 3 is representing subthreshold. Okay. So whenever you are designing a circuit and you are checking the region, okay, which region the MOSFET is occurring, okay, we will simulate that, okay, as per VGS will be moving on, as that you are sweeping the VGS, you have output, you will check it, your MOSFET in which region, for this value, for that value, for that value, we will check it. Okay, and we will find it, okay, region 3, there is no region 0. Okay, why this is? Because cadence is understanding that ideally that region 0 is cut off, but practically we always find it region 3. Okay, so this is the way. Okay, so simulation and understanding have some space. Okay, always think in a way you are understanding the concept. Once you go for the simulation, that simulation will provide a lot of effect. Okay, in this equation you will find only mu and Cux W by L VGS minus VTH into VTS minus half VDS square. But practically, if you go for the scripting and a skill language, in a cadence, they are writing the equation, they are writing lot of thing here. Yes, so that's why that will provide accurate answer. Okay, because they are directly used in your real circuit designing. Okay, so this is helpful for your understanding. You can understand the concept, you can analyze your circuit, and you can find that approximate your answer. To make it fix, you use a tool. Okay, so this is the way that ID is equal to half mu Cx WL by L VGS minus VTH ka whole square. Let's talk about that current. That okay, and next class we will simulate this on cadence virtuoso. Okay, and I will check that how that MOSFET is showing this equation and this values. Okay. So ideally before VTH, what I am doing, I am just sweeping that VGS, means you have a MOSFET, let you have a NMOS, and you have a gate to source voltage where the source is grounded. I am using drain to source voltage that is fixed. Okay, and I am sweeping this. I am sweeping the gate to source voltage from some value to some value, from 0 to some value. Let you are using a GPDK 45, so you are going from 0 to 1.2. Of course, you must have understanding. If you are using a GPDK 45 or GPDK 90 or TSMC of any technology node, you have some manual file. You have a nominal voltage. You can't use 5 volt or 10 volt or 20 volt. Okay. So that have a nominal voltage, how much amount of voltage you can use. So if you're talking about that 45 nanometer technology, we can use till 1.2 nanometer, 1.2 volt. So let I am just thinking a way, okay, you are sweeping 0 to 1.2 or 0 to some 1 volt. So before VTH, ideally that the current is 0. Before VTH, that ID is 0, that is called cutoff. And after VTH, that current is moving like this. And then after that. So interviewer interested on that question. Okay, they just simply say that please design a input, that ID versus IV graph, that is input voltage is varying, where that determine that what is the ID, that output current. Why not input current? Because the input current is 0, because the input impedance is infinite. So as per the tweaking of the gate to source voltage, you are focusing on the ID, the drain current. Okay. So that current is like looking like this. So he or she will interested. Okay, what is happening after VTS? It will be a linear region or it will be in saturation region. The question is asked in a way कि if VGS is below than VTS, that means that MOSFET in cutoff. This before this point, that MOSFET in cutoff. But after VTH, what is happening? It will be entering in a linear or it will be entering in a saturation. So I am just thinking in a way, let VTH is some 0.1 volt and let VDS is some value is 0.3. Let I am assuming this is fixed value, it is 0.3, and you are sweeping that VGS from 0 volt to 1.2 volt. So as per the equation, VDS should be greater than equal to VGS minus VTH for a MOSFET in a saturation region, or VDS is less than VGS minus VTH for linear region. That VGS is increasing. Okay. So as I know, let anyone, that is 0.3 is here, this is greater than VGS minus VTS is 0.1, and I can say that this is 0.4 less than equal to VGS. I am just thinking in a way कि after that 0.1 volt, that if this is 0.4, I am just thinking this is 0.4, this is the point when it is 0.4 here. I am just assuming this. Okay. So if this is the value, VTS is 0.1, VDS is 0.3, and you are thinking that if you are using that saturation condition, VGS should be less than 0.4. In between this range, that this is the point that MOSFET in saturation. In between this range, this is the MOSFET in saturation. Yes, everyone, please understand this part. Most of the student tell that answer after VTH MOSFET enter into a linear region. No, dear. After VTH, MOSFET enter in a saturation. Why? If VDS is some value and VGS is going on, VGS is increases, VDS is fixed. So the drain to source voltage is fixed. As per the gate to source voltage increases, that most of the chance it will be follow after some voltage of the gate to source. Yes, dear. After VTH, the MOSFET enter in a saturation region, and some value of that VGS, MOSFET enter in a linear region. Yes, everyone. Yes, anyone have a question? Sir, I wonder if MATLAB sibling is useful for analog mixer. Yes, they are currently using old technology XH018. Okay, no problem. If you are using a 0.18 micrometer, that is 180 nanometer, that is okay. Don't worry about it. The technology node is not that much important for your understanding. You are using 180 nanometer or 90 nanometer or 45 nanometer, there is no meaning there. If you are good in 180 nanometer, you take mostly 15 days. That maximum 15 days is okay. You will be comfortable of any technology node. Okay, so don't worry about that. You have a 180 nanometer or 90 nanometer or 45 nanometer. There is no problem. Okay, if you are a layout designer, that will be a problem, because as per the layout, if you are talking about 180 nanometer, they have a good amount of that is range. Okay, that 180 nanometer have some good amount of spacing, have an enclosure, but as per the lower technology, that have a lot of rule is introduced. Okay, so that in a layout term, I can say that if you are using a lower technology, that will be helpful for you. So whenever you are designing your resume, that you are specifying, okay, so which technology node you are using for a layout. Okay, in a layout term, that is very important. But if you are an analog circuit designer, there is not that much effect in your understanding. You will find that same thing. Okay, that not same thing, of course, have a channel length modulation is more in 45 nanometer as compared to 180 nanometer, but that is okay. Okay, so here don't worry about that technology node 180 nanometer or 45 nanometer. Okay, let's talk about this part. So I am just designing IV curve, that is ID versus VGS. So before VTS, the MOSFET is behave like a cut-off in NMOS region. This is NMOS, and after that VTS to some voltage, that will be a what? Or I can say that if you want an exact value, I can write it that delta V plus VTH. What is the meaning of delta V? Delta V is represented your VGS minus VTS, that is overdrive voltage. This is called overdrive voltage. The overdrive voltage is the point where the MOSFET in a pinch off. I am not going for a solid state, that's why I am not explaining this part. Otherwise, if you are interested, we will. Okay, so that is pinch off point where that you will find the taper shape. On the drain side, you will find the taper shape. On the source side, you will find the more amount of charge. And as per that VDS is increases, your channel will be shifted towards source side. And here you have a large amount of electric field will present, because E is equal to V by L or delta L. So electric field is very high. So charge will transfer with a high electric velocity, high electric field. And if that you have a high electric field, you know the drift velocity Vd is equal to mu E. If the electric field is very high, the drift velocity will saturate. That means your charge transportation will saturate, the current will saturate. That is the process of the current saturation. But I am not going for this. I am just explaining in such a way in terms of analog circuit designing. In analog circuit designing, we always think MOSFET is a device. I am not interested what is happening inside it. If you are an analog circuit designer, I am not bothered about what is happening in the MOSFET. I am just focusing on what is the gate, what is the source, what is the drain, what is the body terminal, what is the W by L. Nothing else. If you are interested, if you are trying to become a good analog circuit designer, you can go for inside that, and you can find it okay when that this will be a saturation region, when it will be happen in a linear region. The linear region means that the overdrive voltage is not that VDS is not equal to VGS minus VTH, it is less than that. So current can flow from VDS, that current is flowing in terms of that current is controlling by the voltage. That is a linear, that I and V is terms of that is called triode region. Okay, that I is equal to V by R, where that R is R channel. Okay, but once you talk about saturation region, if that VDS is equal to VGS minus VTH, that is overdrive voltage, the channel will be tapered. Why? Because as per you are providing, okay, just think in a way, okay, can be, just think like this, okay, okay, you are providing drain voltage, you are providing source voltage, you are providing the gate voltage in such a way, if VDS is greater than equal to VGS minus VTH, of course that VGS should be greater than equal to VTH. Firstly, you have a channel. You have a channel. Okay. You have a channel as per the VGS is greater than equal to VTH, that the channel is present, that the electron is present here in between N plus and N plus. As per the drain voltage increases, what is happening? If the drain voltage increases, just think in a way ki okay, you have a N and you have a P, okay, this is a P substrate and this is N plus. N plus have a majority concentration of electron and P have a majority concentration of the hole, but the N plus will represent in a way that majority concentration is higher than majority concentration of the hole. And if you are providing that supply like this, means drain side you have a higher potential and source side is lower potential. So what is happening? The depletion region will form. So the depletion region is formed. So the depletion region is lesser shifted towards N plus side, but it is shifted higher towards right side. Just think in a way, okay, you have a 2 room. In one room you have a thousands of people and another room you have 100 peoples. The majority concentration of electron is higher as compared to majority concentration of hole. So that they have thousands of people, they have hundreds of people, and if you are pushing one of that, so 1000 people will not be shifted as much as compared to 100. So if we are reversing this, the depletion region will increases, but the depletion region shifted towards whole side. Means if you are increasing this VD, so the depletion region or anything color, different color, yes. So the depletion region is shifted towards P side as compared to internal of the N plus. So as per the depletion, that depleted the channel, means this channel is not looking like this. So this will be the channel, and this is all our that is hypothetical. This is the way. The channel is shifted like this, and this is the way. So channel is shifted. Why? Because this region is depleted. the channel will wash out. And if there is a immobile ion, they are not conducting ions, they are immobile. Okay. So what will happen? This is a delta L and this is full L, that is channel length, and the shifted towards left side, that will be a delta L. And so it will be what? That is a immobile ion. You have a charge here and you have a charge here. It will be formed at two plates, two conducting plates. So of course it have an electric field here. The electric field is equal to E is equal to V upon delta L, yeah, V upon L. Here is that delta L and V is VD, VDS. So if delta L is very small, the electric field is very, very high. And if you know the relation of the drift velocity and electric field, so the drift velocity Vd is equal to the drift velocity, that Vd is equal to mu E. Vd is directly proportional to E and the proportionality constant mobility mu. So Vd is equal to mu E. Electric field increases, but the drift velocity will saturate. The velocity will saturate at a time, and that what will happen, a constant charge will be passed here, okay, due to high electric field. Okay, that is just like avalanche breakdown is happening here, and the constant current will flow, and that is called saturation region. Okay, so this is the way you can understand. Okay, this is the solid state part. If you know, that is very good. If you don't know, so please work on it. You can go for the solid state book, that is Statement and Banerjee. Statement Banerjee. Okay, or otherwise you can use what, Milben Helkias. Okay, so you can follow that books. Okay, for VTS, that MOSFET in a cutoff, just after that MOSFET enter in a saturation region. That's why this is representing that a square, that a parabola. And after overdrive voltage, that is delta V plus VTH, the delta V is 0.1, 0. That VGS minus VTH or something like this. This is the way I am just writing the delta V plus VTH. After that you will find that MOSFET in a linear region. Yes, is it okay? Yes, everyone. So this is the way you can understand that ID versus VGS. Okay. Let's talk about the for different VDS. That is also very important, and let's talk about different W by L. So in ID versus VGS, that this will be a graph. Okay, this is for some VDS. Of course, this is some for VDS. Let this is VDS1, and I am talking about, let this is VDS2 here. So this is that way. Yes, hello. Okay, and similarly for third VDS2. So if you talk about that, you have a different VDS. I mean, this is VDS1 and VDS2 and VDS3. This is VDS1. This is VDS2, and this is VDS3. So that current will be increases for same gate to source voltage. Let I am thinking in a way कि for same gate to source voltage, let this is a X voltage of gate to source. For same gate to source voltage, you have a different current. So at this point you have a some voltage, some current, At this point you have a different current, at this point you have a different current. So I can write in such a way, this is I1 due to VDS1, this is ID due to I2, this is due to VDS2, this is I3 due to VDS3. So your drain to source voltage here increases and your current will be increases because you are moving your VGS in this way, and you can find it that as per VDS will increases, you can find your drain current. Okay. Similarly, if I am talking about W by L, okay, so this is so as per the different W by L, let this is W by L of 1, this is W by L of 2, and this is W by L of 3. So if the W by L is different, of course that current will be increases. Okay. So for same voltage of that VGS, you will find that same, that different current, that it is I1, this is I2, and this is I3. Yes, is it okay? So in the next class we will simulate this ID versus VGS, ID versus VDS. Okay. So firstly I will cover ID versus VDS, then I will go for the tool. Okay, and these characteristic is very important. Mostly student, they are thinking like this, okay, this characteristic is normal, that ID versus VGS like this is very normal. But no, there once you go for the amplifier and if you are going for a current mirror or differential pair, you can understand your region by the help of these characteristics only. If you are good in characteristic, you can explain that common source amplifier or drain amplifier or gate amplifier or any amplifier by this only. Okay, we will work on it. Okay, so please be focused on this part, and in the next class we will simulate on a cadence virtuoso of ID versus VGS with respect to different VDS. Firstly, you can understand cadence virtuoso, how you will invoke the cadence virtuoso, and then you can use your different short command or different keys, and after the schematic editor window we will design that schematic, and we will go for the AD assembler or explorer, where we use as analysis the DC analysis or transient analysis. They're just same like LT Spice. In a LT Spice, that is, of course, it is a open source, so everyone can use, but cadence is not. Cadence required a license, so we will work on it. Okay, so in the next class we will simulate these equations, simulate this current waveform, and then we talk about ID versus VDS. So till now, please work on it, and these are the fundamentals. As per this fundamental will over, we will go for CMOS inverter and digital logics, or that is common source amplifier. Okay, so for today, thank you so much, dear. Thank you, dear.